Okay, so here's where we were last time. Quick announcement. I do have homeworks to return from that y'all turned in yesterday. So if y'all will help me remember at the end of class, I'll pass those back. Okay, so we were talking about graphs last time, and so specifically, here's how you form the graph of a single variable function. So single variable function, one real number in, one real number out. And the process is to take your function and set the output values. Right, those are the output values from the function. Here's your function. There's the formula for how to compute it. Take the output values, set it equal to a new variable that you make up. Right, so you make up a new variable, set it equal to the function. That's introducing, note now, two variables. It's a little weird if you really think about it. This is a single variable function. Single as in one. Now there's two variables. That's an eyebrow raiser. It's a little bit weird. But that's part of the process. So you set it equal to y, and then you look at the complete set of solutions to that equation. Right? So that is a process by which you can take a function and turn it into a picture. Okay. All right. We talked about that last time. It's very, very similar for multivariable functions. So you got a multivariable function here. Right? N inputs, M outputs. Take the output values. Now keep in mind there's M different output values here. Right? This is the target is Rm. So there are M different output values, and you take those output values and you set them equal to, again, new variables. So these are, you make up variables called y1 through ym, and you set the output values of the function equal to those new variables. Okay. And then you look for the complete set of solutions to these equations. By the way, note plural. This is multiple equations because there's M different variables here, each of which is being set equal to some expression. Right? So that's actually a bunch of equations. Now, here's the good news. The good news is that most of the time, as far as Math 212 is concerned, M will be 1. And so this will be just y equals each of these other variables, and there will therefore be just one equation. Most of the time. Okay, a couple of exceptions. Okay, so what does this look like? Let's think about this function here. Right, f of x1 comma x2 is x1 plus x2. Multivariable function. Right, it's a function from R2 to R1. We have two input variables, and out comes one number for which we have a formula. Easy formula. Okay. So we take that value of the function, we set it equal to a new variable. I'm going to call it y arbitrarily. It doesn't really matter. And so we get an equation, and now we have to ask what is the set of solutions, what is the complete set of solutions to that equation. Now, see section 2.2. Right? There's three variables here. It's an equation involving three variables, and so now you have this task of an equation involving three variables. How do you draw the solution set? Conveniently, this is an easy one because we know from chapter 1 that it's a plane. Right? This is an equation of a plane. And it's hard to draw that particular plane, but it looks something kind of like this. It goes through the origin, and its cross-section with the that x1y plane is that line. The cross-section with the x2y plane is like that. So it's kind of a plane that's coming up out of the page, if you will. Okay. All right, here's a more geometrically interesting example. Here is a function from R2 to R1 again. How do I form the graph of this function? Well, it's the same process. You take the output values of the function, you set equal to a new variable. Now, you've got to be careful in your choice of the variable. The formula for the function is x squared plus y. You can't set it equal to y. It's not a new variable. Y is already an input variable. Right? So we're going to call it z. Just alphabetically. It seems natural. Right? So now again, we have ourselves with a section 2.2 problem. We have an equation involving three variables. We want to know what the solution set looks like. This is a less easy example. It's not terribly bad, but you definitely have to think in terms of cross sections. And you can tell at a glance that if you set y equal to a constant, notice that you get various parabolas. Right? So when you take cross sections perpendicular to the y-axis, you're going to get these parabolic curves like that, and etc. Chapter 2 problem. I'll let you guys think through the rest of the details. And the punchline is the graph ends up looking like this. So this is the set of solutions. Let's say this two different ways. That is the set of solutions to that equation, and therefore it is the graph of that function. Everybody on board? So please be careful with the language. The language is very important. Please don't call it the graph of this equation. That doesn't make sense. Graph is it's a very specific process that says you've given me a function and I'm going to go through the 3-step process. I'm going to create a new variable. I'm going to set the output values equal to that new variable. I'm going to draw the solution set. It requires that the input be a function. You can't really talk about the graph of an equation. You can talk about the solution set to an equation. Likewise, please do not call this the solution set to a function. Again, that doesn't make any sense. A function is not an equation. Okay. All right. Okay. There's a couple more examples in there y'all can take a look at. I do want to talk about one more example real quick, and we're going to move on to the next section. And that is, what if you have a function from R2 to R2? Now, at a glance, this does not look like a particularly intimidating problem. 2 input variables, 2 output. It's barely bigger than 1. Right? This is as easy as a multivariable function could get by being multivariable in both the domain and the target. Not scary looking. And yet, here's the problem. We cannot draw the graph. Can't even dream about drawing that graph, because there are 2 input variables that are, of course, going to be involved in our equations. There are 2 output variables that are going to get set equal to those the values of the function, and so grand total, there's going to be equations involving 4 variables. An equation involving 4 variables would have a solution set that's some sort of weird surface of, what does that mean exactly, but inside of a 4-dimensional space. We can't do it. Not on the table. Does that make sense to everybody? So this is one of the big reasons that I'm not a huge fan of the graph construction. Again, let's not take that out of context. I love the graph construction. It's great in its limited ways, right? But it's so limited. So what I'm not a fan of is the idea of relying on the graph construction. It is so limited. There's barely any examples in multivariable calculus where you can even draw a graph. And I think this is a nice illustration of the problem. Okay, so don't just rely on graphs completely. Here's a different kind of construction. Reasonable question comes up. You need to understand multivariable functions. It's awfully handy to have pictures to work with. Geometric intuition is a powerful human characteristic, right? How can we use human geometric intuition if we can't draw pictures? We want to draw pictures. So the level set construction is a different way to generate a picture that in a natural, precise way correlates to a function. Here's the process. It is not the same as the graph process, graph construction. So it's important to see the difference. Given a function from Rn to Rm, and most of the time m will equal to 1, I'm going to say usually. Well, let me just not write that down. But anyway, most of the time m will equal to 1. You take the output values of the function, and you set them equal to, God, that really sounds like the graph construction so far, doesn't it? Take the output values, set them equal to. The only thing that's different is you don't set them equal to a new variable. You set the output values of the function equal to a constant. That's a very different algebraic process. Right? So set it equal to a constant. That again gives you an equation, and again you can talk about the set of solutions to that equation. And that will generate a different kind of a picture. So these are called level sets. I'll explain in a few minutes why they're called level sets. First observation I'll make is that note that this set, and let me point to this equation here. Let's look at this equation. How many variables are there, and what are the variables that are in this equation? The only variables in this equation, keep in mind, C is a constant, not a variable. The only variables in this equation are the variables that were the input variables to the function. So this is an equation involving variables in the domain. That means that the solution set is a set that lives inside of the domain. Right? Now that is different from a graph. It's importantly different from a graph. If you have a function from R2 to R1, right? So there's going to be, let's say, 2 input variables, call them X and Y, and 1 output variable. You have to have a new variable to label the output variables, right? Grand total 3 variables, and so the graph is a subset of R3, which, you know, really, except for the fact that we're really accustomed to this process, that's really weird. Somebody came to us with a function that has an associated space called the domain and an associated space called the target, and we're going to draw a picture of this function, and if that picture is not going to live in either one of these spaces that came with the function, we're going to make up on our own a completely different world in which to try to understand the function, and that's fine, right? But it's a little weird. The level set construction has no such oddity. If you have a function from R2 to R1, right? And again, let's say X and Y are the input variables, and let's say Z is the output variable. The level sets live inside of R2. They live inside of the domain. Again, that's a space that came with the function. It's not unnatural. It's a very natural thing to do. Okay. Alrighty. A little bit of examples before I do some a little bit more notation and algebra, etc. I want to show you an example that y'all have all seen before of level sets. Assuming you've ever clicked on like weatherchannel.com or any of those things, and you see, you know, map of the U.S. Not the best ever, but I've seen worse. And you know, so it's the Weather Channel, right? And so they're showing you temperatures, and they'll show, you know, so southern Texas and Florida is all in red. And then let's see here, they'll have an orange streak over here for something like that. I don't know. It's probably warmer in Arizona, but anyway, that's not the point. And then there's a streak for, you know, not quite as warm as that. And then maybe it's just downright cool up here, and maybe even cold up there, right? Has everybody seen these kind of pictures? This is, you know, you're watching the weather on TV or whatever. Not that anyone does that anymore. So what you have here is a bunch of level sets. These are level sets of the temperature function. So specific. Now they're not going to say that, obviously, right? But they'll do stuff. They'll say stuff like they'll label this as 90s, and they'll label this as 80s, and you know, 70s, 60s, and 50s. Sure, right? What they're saying then is that this curve right here. Oh, I shouldn't do that in that color. Here, let me. I'll use black. That's fine. This curve here. That's where temperature, as a function of position, is equal to 90. Now this curve here, that's where temperature, as a function of position, longitude and latitude, is equal to 80. Right? Those are level sets. We have a function that we've set equal to a constant, and we're drawing the points that satisfy that equation. It's a level set. It's straight out of the definition. Right? So I guess what technically they draw the space in between the level sets, but I mean implicit in there is that you're looking at level sets. Yeah? Everybody good? So now let's think about the alternative. I mean, what else could the Weather Channel website, or whatever website, how are they going to communicate to you graphically what temperature is doing in the United States, right? Well, they could take this temperature function and draw a graph. Now let's think what the graph would look like. It's a function from R2 to R1. There's 2 input variables. There's 1 output variable, namely temperature. That's 3 variables. The graph would be a surface. So they could like 3D print or make a hologram of the graph, right? And then they could like, here it is. And you're looking at it from a weird angle and you see this great big peak up here and you think, oh, well, it sure is hot over there. Okay, well, what point is that on the map? Hard to tell what that's directly sitting over when you're over there, right? And of course, if they turn it like this, then you can't see the heights very well. It's just awkward, right? This is really a much more convenient way to understand what temperatures are looking like. That's why they do it. Or said differently, that's why in many contexts, this one being one, level sets are superior to graphs. They communicate information, in some ways at least, quite a bit more efficiently than graphs. And we're going to see many other examples. All right, everybody on board so far? Okay. All right, so by the way, there's a little bit of lingo that goes along with this. The curve showing, where the temperature is all the same temperature. The curve where temperature equals 90, that's called an isotherm. Other people talk about isotherms. That's just level sets of the temperature function. Isobars, if you're doing a similar thing for barometric pressure. And in general, whoa, what did I just do there? In general, hang on a second. In general, if there is some quantity that you're interested in understanding, how it's a function of whatever your variables are, these curves are sometimes called isoquants, depending on the context. Okay. All right. Now here's a different way to think about level sets. I'm going to erase my pretty picture here. See, I guess this is the easiest way to do that. Okay, so keep in mind, if you have a level set, we're talking about a function. Very often I like to draw functions by explicitly drawing the domain and the target, so you can see the process. I mean, here's what the function is doing. Right. So a little bit of lingo. We've talked about the word image at some point in the past. So outputs from the function are called images. So if this is a point A, then whatever the value of f is, so f of A, we call this the image of A. So the function goes that way, right? Here's an input. The output is called the image. And by the way, I'm a big fan of the kind of the metaphor here. The metaphor is that the function is like pushing it that way, and this is where it, this is where it ends up. So I think image kind of communicates that. So on the other hand, you could ask a different question, which is, suppose you have some value there. You could ask, okay, what are the points in the domain whose images are that value? It's almost like we're saying, hey, I've got an output value, and I sort of want to move backwards through the function. Sloppy language, forgive me. But I sort of want to move backwards and find the things that land on there. And so that would be some points, whatever. Maybe a curve like that. All of the points of which have the feature that the output value is exactly that value C. Well, the notation for this, I think, is extremely reasonable. If you have an input, you want to know the corresponding output. We talked about F. If you have an output and you want to know what are the corresponding inputs, we talk about F inverse. And it's a little bit of awkward in notation. Let me write this down first before I criticize it. So these points here. we refer to that as f inverse of c. Now, it's very natural in the sense that, yeah, we start with an output, we want to know what the corresponding inputs are. We're going backwards through the function, so it's f inverse makes a lot of sense. The awkwardness is that we're using a notation that suggests that this is a function, and of course it probably isn't. Certainly in this case, it's not a function, right? It is not the case that functions are rigidly defined things. You can only have one output value for a function. If there were an inverse function, f inverse of c would need to be a single point, and here it's not. Here f inverse of c is all this entire curve here, all those points. Okay. So, okay, it's not a function. This notation is suggestive of something that isn't true, but everybody knows it. Everybody accepts that, okay, yeah, it's awkward. Interpret it appropriately, and this is what people write down. Okay, so notice this is just another way of writing the set of all points for which f of x comma y is equal to c. In other words, this is just an alternative notation to represent the level set of this function defined by that output. So it's an alternative notation for level sets. And you'll see I've used that over here. This is that same notation. These are various different level sets of a certain function that we're about to talk about. Okay, so let's look at this example here. We have that function. Now we drew the graph of this function last section. The graph is this plane that's angled up, sort of coming out of the page in R3. Hard to draw. Now let's say, okay, instead of trying to understand this with graphs, let's try to understand this function with level sets. Let's draw a few of the level sets. Now keep in mind what a level set is. A level set is, what do you get when you set the value of the function equal to a constant? Pick any constant. Pick several constants. So f inverse of 0 is what you get when you set the value of the function equal to 0. Note that that's a line in R2. F inverse of 1 is what you get when you set the value of the function equal to 1. That is also a line in R2 as it happens. Right? So you can go through this process, keep going, generate as many level sets as you'd like. And here's a bunch of level sets. So here's a picture including a bunch of different level sets that in its own way is helping us understand that function. This is not a graph. Right? It's very different from a graph. The graph of this function is a two-dimensional plane in space. Here we have a bunch of lines in R2. Completely different picture, representing the same function. Yeah.
But how do we know that the slope is
Yeah, well, it's just a little bit of old high school algebra. That, in other words, if you look at these equations, right, solve for one variable in terms of the other. You can think of this in mx plus b format, or you can think of this in ax1 plus bx2 equals c format. Right? It's just yeah, yep. Okay. Okay. So again, I emphasize this is not a graph. It'd be really confusing if you were to refer to this as a graph of f, because it's totally different from the graph instruction. Nevertheless, this gives you a way of understanding that function. Right? What's this function? F of x1 comma x2 equals x1 plus x2. What is that function doing? What does it look like? This is telling you, in some sense, some of that information. It's telling you, well, here's where the function is 0. Here's where it's 1. Here's where it's 2. And that communicates information, just like the weather map did, yeah.
One of those lines is a level set, and all of them are the level sets, right?
Yeah, sure. That'd be a fine way to say it. Yep. And of course, you can't draw all of them. If you draw all of them, the whole picture would just be solid ink, right? And so, by the way, that is one of the weaknesses of the graph construction. It does not convey absolutely 100% of the information about a function, right? Where's the function equal to pi? That's not indicated on the picture, right? There is no f inverse of pi on here. I didn't draw that one, right? You can only draw some of them. So So the level set construction has the advantage of being lower dimension, right? Easier to draw. It has the disadvantage of it just doesn't communicate everything. On the other hand, let me now, in its defense, note that when we try to draw this graph, this doesn't communicate anything, every bit of information about the function either. This is a different function. But I draw, this, my attempt to draw with a pencil, this shape, right? This shape, I guess you could say, conveys all the information about the function, but my drawing of it didn't, because there is nothing on the paper right there. That's a clean spot of paper. There's no information being communicated there. I've drawn the outline of a folded piece of paper, and your imagination's supposed to fill in the blanks and be like, oh, I see what's going on. I think I have an intuition for what's happening there. But it's not on the page. Right? So drawings of graphs are arguably even less communicative than level sets. Anyway. Okay, so it turns out there is a relationship between graphs and level sets. Now, it's not a perfect relationship. Again, they're certainly not the same things, but I do want to talk about what the connection is. So here we have a function f from R2 to R1. Let me write that down first. And we have drawn here the graph. So see here I've set the function equal to a new variable z. That gives me an equation for which I can draw the solution set. And I've just, hypothetically, let's suppose, depending on what the function is, maybe the graph looks like this. Some surface. Okay, so there's the graph of a function. Let's consider now what would happen if we took a horizontal cross section So horizontal cross section there of our graph. And I appeal to your geometry intuition. That would make a curve kind of like that. Right, now, I claim this has something to do with level sets. And the way you can see that is, notice that we've set f equal to z, but then we set z equal to c. So grand total, in effect, we have set f equal to c. And setting f equal to c is exactly what you do when you make a level set. Oh, this won't quite fit on the page. Right, so that cross section of the graph, let's see here, let me do it like this. So that and that are both characterized by f of xy equals c. So, nice way to say it then, geometrically, is that horizontal cross sections of graphs relate to level sets. Everybody happy with that? So again, they're not the same. The graph is a surface in space. The level set is a curve in the plane. They're different things, but they are related by way of this cross-section process. Now, I say related. There's a temptation to say, well, aren't they exactly the same thing? Not quite. Technically, if you think about it, the graph being a surface in space, the graph is in space. The cross-section is in space. This is a bunch of points with 3 coordinates, right? The third coordinates are all C. Okay? The third coordinates aren't interesting on this red curve up here. But nevertheless, these are points in space. They have 3 coordinates. The third one is boring. But it's technically not the same as a bunch of points with 2 coordinates. But the x's and y's described here are exactly the same as the x's and y's described here. So very closely related. Okay. Here's an example. You can I think this is a helpful example. Let's look at this function. We've already studied the graph of this function. Right? The graph is what you get when you, let's see here, so the graph, what you get when you set that function equal to a new variable, for example, z. And notice that, of course, just, z equals x squared plus y squared is a surface that we've talked about. We went to a bunch of trouble last time, I think it was, we talked about rotational symmetry and that kind of cross sections, etc. So we know what that is. That's a bulb. Okay. However, let's take this function now and talk about its level sets. Well, again, level sets are what you get when you set the function equal to various constants. So let's, instead of setting x squared plus y squared equal to z, let's set x squared plus y squared equal to c. Think about the different values of c. What kind of curve? Note these are curves in the plane. Right? What kind of curves do you get depending on what c is? Not hard to persuade yourself. This is a bunch of circles, right? Depending on c. In fact, the circles where the radius is clearly the square root of c. Think about the form of the equation of a circle. So we have the level sets look like this. A bunch of circles centered at the origin, various different radii. And if you think about it, that's exactly what you would expect in taking horizontal cross sections of the graph. Right? The graph we already agreed was this paraboloid. Horizontal cross sections give you these circles of radius square root of c. Okay. Here's another nice thing about level sets. The dimensional advantage is pretty awesome. So, for example, let's think about here's a function from R3 to R1 defined by that formula. How would we draw the graph of that function? Well, this is not unlike an example we talked about in the last section. There's 3 input variables that participate to compute about 1 output value there. So we have 3 input variables, 1 output variable. Grand total 4 variables. The graph equation is an equation involving 4 variables. It lives in 4-dimensional space. We cannot begin to dream about possibly drawing such a picture. So the graph is inaccessible to us as mere 3-dimensional people. The level sets are not that bad. The level sets are what you get when you set the value of the function equal to various different constants. Right? You set the value of the function equal to various constants. You get these equations. Those are spheres of radius square root of c. You get various spheres centered at the origin. So I can draw, at least I can make a decent drawing of a bunch of level sets of that function. This is a picture. Yeah, we could argue about how good or useful this picture is, but it's an actual geometric picture that I can draw with a pencil. Right? So level sets give me something to work with. The graph construction gives me nothing. So, big win for the level set construction. Everybody on board?
So what's the difference between the level set and the cross-section?
Yeah, so that's just, the only difference is where they live. Let's go back to this picture here, and unfortunately I have to zoom out twice, but I think it's fine in this case. So a horizontal cross-section of the graph is a curve that looks awfully similar to the level set. And again, the values of x and y here and the values of x and y here are same, x's and y. The only difference is that these are points in R2. These are points in R3 with a third coordinate z. Boring though it is there. And so it's, if you want to say it's the same curve living in a different world, that'd be fine. But technically they're different. Yeah. Okay, let's see, where's my thing? Here it is. Here it is. Okay. All right, so there's here we go. A couple other really nice things about level sets. First observation I'll make along those lines. Any equation. That's a pretty good start to a sentence, right? Any equation, that big reference. Any equation that you have, the solution set can be expressed as a level set. So anything that we come to understand about level sets, by the way, eventually we'll be doing calculus. Anything that we might learn about how to interpret calculus in the context of level sets is going to help us understand any equation. Right? The calculus of level sets applies to any equation. Now, of course, you've got to pick the right function, and the idea here, we've talked about this idea before, but whatever equation you might have, you have an equation like that, you can just, take everything that's on the right, whip it over to the left, and notice that what you end up with then is stuff equals 0. And notice that this function then, notice that we're talking about a level set of that function. So, the trick of take the stuff on the right, turn it over to the left, gives you a level set, and specifically a level set of that function. This is going to be a very useful trick. It is very common to have an equation that you want to understand, right? And so being able to realize it as a level set is going to be a neat trick. We are going to learn some neat things about the calculus of functions as visualized in the context of level sets. Very valuable trick. Okay. Related trick. For any function, the graph of that function can be viewed as a level set. Now, let me emphasize what I'm not saying here. I'm not saying that the graph of a function is the same as a level set of that function. No. I'm saying that the graph of f can be viewed as a level set of some other function. Right? So, different function. Nevertheless, this can always be done. The reverse is not true. Graphs can always be viewed as level sets, not vice versa. So let me show you how this works. First observation I'll make is that this pair of equations here are identical. I mean, effectively. Morally the same equation. Just take this, move it over to the other side. It's a trick we already pulled. And then just realize that, well, in fact, this first equation is describing the graph of the function f. Just, that function f there. Because it's variable equals function. Okay. On the other hand, notice that this other equation down here, we are looking at a level set. You can see that it's a level set because we've got stuff equals 0. Now, is this a level set of f? No. Critically, no. This does not say f equals 0. We've got this new expression over here. It's not f. It's y minus f of x1 through xn. So this is a new expression. It doesn't even have the same number of variables as the function f. This has more variables. There's the n variables that came with f, and then there's the extra one, y. Right? So this function, I'm going to call it g. This is an expression involving n plus 1 variables. Right? It's x1 through xn and y. There's a simple formula for it. Right? It's a function of rn plus 1. So, a graph of f is a level set of g. Everybody see how the trick works? It's morally equivalent to the trick that we pulled a couple pages back where you need to take all the terms on the right and just kind of toss them over to the left, and now you got stuff equals 0. That little tricky little move allows you to interpret every graph as a level set. Now again, this is going to be valuable. Sometimes you'll be given a surface, it'll be written as a graph. And we will, by the way, understand soon calculus in the context of graphs in certain ways, right? But the way calculus looks in the context of level sets is different, and sometimes in a really useful way, in a way that's really awkward. And if you're thinking of something as a graph, can be that the calculus is just not what you need. You need to be able to reinterpret it as a level set, and this is the trick that allows you to do it. Whatever function whose graph you're looking at, pull this little move, note what the thing is that's being set equal to 0, There's your new function, and it in fact, it is a level set of that function that is your old surface. And you can then use whatever you know about the calculus of level sets. Okay. All right. Okay, bunch of exercises. By the way, let me say the terminology, again, is really important. Please be very careful with the terminology. Standard mistake is to talk about graphs of the level set, for example. That doesn't make any sense, right? We're talking about, this business about horizontal cross sections of graphs equaling level sets. Often students will talk about level sets of the graph. That doesn't make any sense, right? If you have a graph, you can talk about a cross section of it. You can't talk about a level set of it because level set construction applies to functions. Right? So you got to make sure to use the terminology right. And be careful with that. I'm going to say that a bunch more times because it's really important. But anyway, okay. So be careful with that in these exercises. Okay, we're going to talk about parametric curves. Now we'll get to surfaces soon. Parametric curves first. It's another way to relate pictures to functions. We'll start by defining something called the image of a function. The image of a function, yet another picture that we associate to a function, and it's the set of all output values of the function. Actual output values that are realized from actual input values for the function, right? Something that has in fact come out after something specifically went in. Okay. Let me start with a picture. Let's see, do I have some space down here? Yeah, okay. Let me start with a picture. So, domain, target, call this function f, let's say, and let's think about, okay, so you got 0, and then over here we have, let's say, f of 0. Okay, now, that's an actual output value. That came out of the function when I put that thing into the function, so this is part of the image. All right, now let's move over in the domain a little bit. Here's a nearby input point. Now you'd probably expect the output point to also be nearby the original output. Maybe that's f of, I don't know, 0.1. I'm just making something up here. And then another nearby point, you might expect that to be nearby, and another nearby input and another expected nearby output. And you might imagine that as you sort of move through the domain, every time you move a little bit, you get a new input point that gives you a slightly different output point, and you could reasonably expect then you get this sort of continuous chain of nearby output points, otherwise known as a curve. Right, so you would expect, now you got to worry about the regularity of this function, is it continuous? Blah, blah, blah. Let's not worry about the regularity. But generically, what most of the time, nice functions you would expect, then the output values to form a curve. Does that seem plausible? Here's another way to think about it, by the way. You think of a function in the same way that a function takes a point and kind of, in a way, sort of picks that point up and then kind of sets it down somewhere, depending on what the function is, right? You can think of the function as simultaneously picking up the entire one-dimensional domain and doing whatever the function does. Maybe it's going to take this line and maybe kind of bend it around or something, but it's going to pick up that entire curve and set it down in the plane. And so, again, you should kind of generically expect it to be a curve. Hope that's plausible. All right. So, a little bit of lingo now. The curve is called the image of the function f. The function is called a parameterization. Of the curve. I'm going to call the curve C, by the way, just to have a name for it. So these words, image and parameterization, they're kind of sort of backwards in terms of grammatical structure. They're kind of backwards of each other. The function parameterizes the curve. The curve is the image of the function. Okay. So together, the curve with its parameterization, we call this curve a parametric curve. That's just lingo. Okay. Let's see some examples. Let's see, did I skip something? Yeah, cool. Okay, some examples. Here is a function, R2 to R1, that formula. And we could ask very reasonably, what's the image of this function? What points come out? You know, when I take real values t and I plug into this function, what points come out? Well, you could, I suppose, take one value of t at a time and plug it on in there and see what points you get and put down a little dot, right? And then you could keep going, and maybe if you're really industrious, you could maybe put in 10 or 15 points, and you'd have 10 or 15 output points, and that's not a very good picture, right? So we'd like to figure out what is the entire image. What are all of the outputs? And the idea is to look at the output variables. There's x, right? And there is y. And let's just see, can we come up with any relationship between these? Can I? Is there any obvious equation that relates x and y, given that x and y are these things? Now, there's no mechanical process for always, every time, no exceptions, algebraically going through and finding what the relationship is between x and y. But sometimes you can kind of see how it might work out. And for example, here with this t plus 1, that doesn't look too terribly different from 2t minus 1. And you could imagine taking t plus 1 and just, how about we multiply it by 2? 2x is 2t plus 2. That looks even more like this. 2x has the wrong constant, but if I then subtract 3, I would get exactly 2t minus 1. So 2x minus 3 is y. So you can kind of cram it in there in some sense, in some cases like this. You're just looking for an algebraic relationship, and this is the one we get in this case. And again, that x and that y are what we're relating. So that really helps, because what that tells us is that these output points, these x comma y's that we're sitting there putting down one dot at a time tediously, they all satisfy that equation. That means that these points that we're looking for, they're all on this line. And it's not hard to persuade yourself. In fact, they are the entire line. So, nice. Handy. So the image of this function is this line here. How we doing? Everybody happy? Okay, here's a different one. Function from R1 to R2. Here's the formula for it. Note how significantly different this function is. It's got cubes in it, for crying out loud. Totally different function. And yet, weirdly, not hard to persuade yourself that being as it is x, and that being as it is y, this equation still holds. Right? This y is, again, 2 times that x minus 3. So this function is a different parameterization of the exact same line, so it would seem. Right? So the lesson here is parameterizations are not unique. Parameterizations are there's lots of different parameterizations of the same curve. There's lots of different functions whose images, let's come back over to this picture. There's lots of different functions that in their different ways would trace out this same curve. All right. Okay. Okay. Now, how do we distinguish these functions from each other? Now, arguably our purpose, where's my, well, I'll just come back to this. Arguably my purpose in drawing images of functions is I'm trying to get a picture that helps me understand this function. And if there's two different functions that I'm trying to understand with the same exact picture, well, that's obviously suboptimal, right? It'd be nice to have, a picture that sort of distinguishes these very different functions from each other. And looking only at the image doesn't cut it. These two examples being illustrating that. So the idea is, let's take a different interpretation of the input variable. The input variable I'm going to reinterpret as time. So I noticed I didn't say that word up to this point. So I've been talking about, functions of, you might have guessed it because I chose to call this t, right? But anyway, I'm going to now explicitly choose to, just for our imagination purposes, let's think of t as representing time. As such then, these two different functions, I can distinguish by indicating where am I at different times. So for example, with this function, yeah, that's the image. With this function, that's the image, same exact image. But with this one, at time equals -1, I'm there. At time equals -0.5, I'm there. You can actually indicate some specific points. Not hard to persuade yourself that this is, straight line, constant speed. In fact, this is a chapter 1 style parameterization of the line. And so we're just moving across that line at a constant speed. Now that I'm interpreting t as time, I can talk about time-related concepts like speed. So this function, you might say, draws this curve at a constant speed like that. Whereas this doesn't. Notice that in equally spaced time intervals, this does not give you equally spaced points, right? So this different function it's tracing the same line, got the same image, granted, but it's tracing that line in a different way. It's coming real fast into 0 and then real fast out of 0, right? It's going real fast over here. Look how far these points are separated from each other. And then as you get closer to t equals 0, it's going pretty slow along in there. And then after you pass t equals 0, it starts to speed up again. So this little annotation, you might say, indicating different values of t is a way to distinguish the pictures from each other. Okay, I like the little snail metaphor, by the way. The curve is the trail of slime that's left by the snail. Yeah, maybe y'all didn't grow up where there's snails. When I grew up in Houston, there's snails certain times a year, and as they crawl over things, they leave this little trail of slime, and it's just is evident, this is exactly where the snail has been. Right? So the curve, the image, is the trail of slime itself. Right? The parameterization is not a curve. The parameterization is a function that tells you where is the snail as a function of time. It's an algebraic thing. I also like, along these same lines, different metaphor, which is we distinguish between a parameterization and its image that's kind of like a road versus a road trip. Right? So let's talk about a road trip. What is a road trip? A road trip is, we get in the car, we start driving, and at any given point in time, we're at some location, but off we go. It's an experience. It's this whole process of we were here, and then we drove around over there, and then we stopped for a little while. We had a picnic, and then we drove along a little further, and it's this process of tracing out a path. The road is not a process. The road just sits there. It was there for decades before you had your road trip. It'll be there for decades, fingers crossed, until after your road trip. So the road is this motionless, inanimate thing. The road trip is the process. So functions, parameterizations are road trips. Images are just the road. Okay. All right. Let's see some examples. I'm going to skip to just a couple of examples. I'm going to do as many as I can, but time's a factor here. So here's one. There's a function. This is a parameterization of some curve. What is this curve? X is cosine t, y is sine t. That probably rings some bells, right? By the way, feel free to take advantage of that if the algebraic structure of what you're looking at looks familiar. Feel free to let that guide you in a certain direction. Here we're thinking, gosh, that reminds me of trig class, right? X equals cosine, y equals sine. Right? And not hard then to persuade yourself that, well, yeah, this is a parameterization of the unit circle, because if you take x equals cosine t and y equals sine t, right? Take the x and the y functions that are given, plug them into this equation, the equation works. Because Pythagorean identity, we know cosine squared plus sine squared is 1. So this parameterization traces out the unit circle in the usual way. All right. Again, you won't always get that lucky. Here is a related example. Let's look at this parameterization. Here we have a function from R1 to R3. So x is cosine, y is sine. That's all familiar. But now z, this third variable, this is not just in the plane. Z is its own function, t. So we can't, it's hard to imagine how we'd come up with some function that involves sine t, cosine t, and t by itself that would encapsulate all of what's going on with this function. It's just hard to see how that would work out. What you can do in this case is just, kind of piece together by what you know about the two different kind of things that are going on here. X and y are familiar. Cosine t, sine t. That means I already know whatever z is doing. We'll talk about z in a moment. This curve is moving around in such a way that in the xy plane, it's just doing this. We got a circle. The point may be moving around in some way, but if you look just at the x and y coordinates, if you project down to the xy plane, it's doing this. Right? Now, z is easy to understand, but in a very different way. Z being t, z is just increasing as time, right? So we're talking about a point that's moving along a curve in such a way that the shadow is going around in a circle, and the altitude is increasing at a constant rate. And you kind of put it together. Not hard to persuade yourself that it looks like this. Kind of a by hook or by crook process. This is the way you can kind of see it in this case. Okay, here's another example. How would I understand that function? Can I think of some algebraic relationship, right off the bat between x and y? Now there's a temptation to say, oh yeah, check it out, x plus y is 2t. It doesn't really fit the bill. That's not telling us a relationship between x and y. That's telling us a relationship between x, y, and t. I'm trying to draw this in the xy plane. There's no t-axis for me to include in that picture. So it doesn't really help to make that observation. I need a relationship between just x and y. Can I square x and square y and everything, somehow the t's magically cancel? No, it's not easy to figure out how you would do that. I don't know how I would do that. So we're going to understand this in a different way. I'm going to understand this as being a sum of two separate vectors. That vector is easy to understand, t comma t, y is equal to x, no problem. And then to that vector, I am adding this vector. And that vector is also kind of not that bad to understand. Negative 1, 1 is a constant. Right? And negative 1, 1, okay, that's not what I'm adding to this, but I'm just multiplying it by sine t. So in that direction, there's going to be an oscillating vector kind of going like that. Right? And I'm going to add, to a point that's moving along the line y equals x, I'm going to add a vector that's kind of going back and forth in the negative 1, 1 direction. And altogether, so again, t comma t on the line y equals x. So this point, t comma t is moving like that. This vector, negative 1, 1, you can see as time passes, I'm going more in that direction or less in that direction or eventually in the negative of that direction, right? As we move along the green curve, as t increases, we'll move along the green curve, but as t increases, sine t is going to oscillate, and that gives you these oscillating blue vectors that I'm adding to the green vector. And so you can persuade yourself that this parametric curve that we were trying to understand in the first place, this, having rewritten it as green plus blue, going to look kind of like that. Now, this is a different process. It's not what we did in the case of the helix, and it's not what we did in the case of the circle and the plane. And it's just, this is just a different idea that's useful in different situations. Okay, parametric surfaces, very similar idea, just one dimension higher. Let's look at this function from R2 to R3, defined by that. Now let's take a moment to clarify here. There's two input variables, u and v. You cannot think of u and v as being time. That's one of the tragedies of parametric surfaces. They're parametric curves. We have this wonderful metaphor involving time. You can think of them as, again, it's a trail of slime, it's the road associated to a road trip, however you want to think about it. Very familiar metaphors. Not so much here. It's u and v. There's two of them. We don't have two time variables, depending on which science fiction movie you're watching. Right? So what we can do, though, is, again, think about these outputs as being different functions. So there's my x, and there's my y, and there is my z. Play the game, try to, can I come up with some algebraic relationship involving x, y, and z? In other words, these three things, can I, in some clever way, figure out how, some combination of, some multiple of this minus some multiple of that ends up giving you exactly that. Any sort of algebraic relationship you can come up with. And if you play with it, in this case it turns out that z is 2x plus y. That's the equation of a plane. So that means that this function f, all of the outputs, so in other words, its entire image sits inside of that plane. And again, it turns out the image is in fact the entire plane. Okay. Not too surprising that it would get a two-dimensional surface. By the way, let's think again in terms of, what kind of thing would you expect? Well, here's a function with, u and v as the inputs, x, y, z is the outputs. And let's think about this one point at a time. That point, the origin, is going to have some image. And then here's a nearby point, going to have some image. And here's a point near to that, and that's going to have some image. But you can go in the other direction. That point going to have some image, and that point going to have some image, etc., etc. That point. Now, what about this green point? Well, going that way, the outputs went kind of that way, but going this other way, the outputs went a different way. I mean, you'd kind of expect that again, you know, we're not proving anything here, but just you'd not be surprised if it turned out that that output were some point kind of in that general vicinity, right? And again, I think it's pretty plausible. If you think of the entire plane being picked up, you know, what does the function do? The function's going to do something. It might bend it and twist it around in some way, but in the process of picking up a two-dimensional domain, bend it, twist it, sure, the result you would expect to be two-dimensional, expect it to be a surface. Okay. Where's my, here we go, graph parameterization. Okay, how do you go the other way? So we've talked about, here's a function, what's the image? Now we're going to go the other way, we're going to say, here's the image, what's the function? Or said differently, here's a curve, how do you parameterize it? Okay. And there's a couple of methods that are really handy. I'm going to show you my favorite two methods. They're morally kind of the same example, but anyway, let's call them two different methods. The graph parameterization is awesome. It's really, really cool. What it says is if you are looking at the graph of a function, you can always parameterize it with the following trick. And here's the trick. If you are looking at a graph, cannot emphasize this enough, this only works for graphs. That's got to be a graph. Y equals function of x, right? Can't be a circle. Circle's not a graph. Just let x, whatever the input variable is, whatever that input variable is, just let it equal to t. And everything falls into place. If x is equal to t, well, if you think about it, if you know what x is, this being a graph, you know what y is. If x is equal to t, plug that in, you get y equals f of t. Right? So y has to equal to f of t. X was t. And now notice you have formulas for position, x and y, as functions of t. It just, like I say, everything just falls into place. It could not be more convenient. And so here's that formula. In general, if you're looking at the graph of a function from R1 to R1, this is the parameterization. So x is t, and oops, color choices. Y is f of t. That'll always work for a graph. Again, it only works for graphs. Here's a two-dimensional version of it. So if you have a function from R2 to R1 and you're looking at the graph, now again, before we go on, let's notice, particularly from R2 to R1, the graph is a surface in R3, right? Because we're looking at a graph, specifically. Same trick works. Just let your input variables be your parameters. Let those be u and v. X is u, y is v, and then everything just falls into place. Hey, if x is u and if y is v, well then z being f of x, y, x and y being u and v, z has to be f of u, v. And so this is a parameterization that will parameterize that graph of that function f. Okay, same idea. It doesn't matter how many dimensions you have, this will always work. Okay, it's a great trick. Here's a variation. This is arguably a different idea, but in a way it's kind of the same idea. This is choosing to view the graph in this way. If you have a graph of a function, you're writing one variable as a function of the other variables, right? So typically we'd say z is a function of x and y. That's what the graph equation is, right? Z is a function of x and y. Well, let's just open this up to the possibility that maybe it's not z that you've solved for in terms of x and y. Maybe you've solved for y as a function of x and z. Or maybe you're in a different coordinate system. Maybe rho is a function of phi and theta. Or maybe z is a function of r and theta. It doesn't matter what coordinate system you're in. If you can write one of the coordinate variables as a function of the other variables in that coordinate system, the same morally equivalent idea totally works. So here's a polar coordinates version of that. Suppose r is a function of theta. Now this is an equation involving polar coordinates, so r and theta is right. But specifically, I have solved for one of the variables, r, in terms of the other variables. So r is written as a function of theta. Everything just falls into place as follows. Keep in mind, x and y, standard formulas. Right? Well, if r is a function of theta, just plug that in there. And notice that what comes out gives you x and y as functions of now just theta. And there's a temptation to say, well, yeah, but there's an r in there, but not really. No, that r, we've plugged in whatever function of theta it was. So if you can solve for r as a function of theta, just plug it in, everything falls into place, and you have position as a function of one parameter. That's a parameterization. Here's a spherical example. Suppose that suppose rho is a function of phi and theta, as it often is. Well, same trick. Here's your standard spherical coordinates formulas, straight out of the section 1 point whatever. Right? If rho is a function of phi and theta, plug it on in there, like so. And now the rho effectively disappears because we've replaced it with whatever function it is of phi and theta, and you have then position as a function of just phi and theta. Okay. Last example is a rectangular example. Now this is a nasty looking one. Here I've got some explicit algebra in here. In this case, I don't even have yet solved for one of the variables in terms of the others. And furthermore, it's not clear that I'm going to be able to do this. I mean, at a glance, that algebra is pretty scary. Let's just take a moment to appreciate how scary that algebra is. Wow, can you imagine trying to solve for x? This would be a transcendental equation. We get x inside of an exponential, but also x outside of the exponential. You can't do that. Algebra is super scary. Likewise with the z, right? And it seems like we're kind of out of luck. Except, check it out, the y is not a problem. You can totally solve for that y. That y is a very conveniently written down function of x and z. And so we have solved for one of the variables in terms of the others. And so play the game, the usual game. The input variables, so x and z. I'm going to let x and z be, oh, here, that didn't do that well, did I? I'm going to let x and z be u and v. All right, just let your inputs be the parameters, and then everything falls into place. What is y? What should I set y equal to? Well, that tells you y is whatever it has to be. Just, you know, you've already solved for it, so just plug in whatever y is in terms of x and z, aka whatever y is in terms of u and v. And there you go. And you note now that you have position x, y, z, all as functions of only two variables now, u and v. Cool trick. So the wonderful thing about this is you look at this equation that we started with, I don't even know how to draw that picture. Right? I don't know what this surface looks like. Yikes. But I can parameterize it even without seeing the picture. So that's kind of cool. Okay, that makes for a great stopping point. We will call it a day here. And we're now officially done with, let's see, I think we did 3 sections today. We did 2.3, 2.4, and 2.5. I'll send out an email noting that those are the sections assigned for today. Today's Tuesday. That means the homework will be due Thursday. See y'all later. Have a good day. Oh, and I've got homeworks to return if you'll stick around for just a moment.